topic or chapter, we have to discuss about mixtures of gases. So before we have to see the chapter one, mixture of ideal gases. Let us starting from what is a gas mixture mean. What is a gas mixture? This a gas mixture. As we have seen, there is two words. One is a gas and a mixture one. So first, what does it mean? Gas mean, or what does it mean? A gas. What is gas indicated? So this a gas is simply we have to see in PV or TS graphs. So we have to getting of this types of graphs. So in a constant of pressures, we have to getting of constant temperature, we have to gain of this type of graphs. So here this line is indicated for a saturated liquid line, and this one is a saturated uh, vapor line. So this regions is compressed liquid, region. This one is a saturated liquid vapor mixture, saturated liquid vapor mixture, and this line is a saturated liquid line, and this one is a saturated vapor line, and the regions here is that is a vapor region. This one is a vapor region. So all of the substance that occur as this regions, that is in vapor regions. So when is the substances that's getting with this regions, that's the saturated liquid vapor mixture regions, and here is a compressed liquid, and the line is also negative for that's the point. So a gas is always we have to discuss about in a vapors region. So a gas mean that's in a vapor region. So this gases is it may be real gases, or let's see ideal gas. So what is the difference between real gases and ideal gases? What is the difference between real gases? That is what is ideal gas means. That real gas means that is the gases that's occurring in natures. So what about in ideal gas? Ideal gases, we have to answer this questions. Is that real gases is occurring in natures, or ideal gases that's occurring in natures? We have to asking of this question: does ideal gases exist in life or in real one? So this answer is no, but there is no, this gas is not occurring in real, but this ideal gases is treated by using of some conditions, whereas that's conditions. So before we have to go in of this ideal gases, let us putting of three question. This three question is help us to understand what ideal gas means. The first one is, as told you before, does ideal gas ideal gas exists in real life or in real one? Second one is, if your answer is no, the second question is we why we study ideal gas. And the third one is, can uh, real gas and ideal gas that follows the PV equal to nRT equations. What is this equation? That follows these equations. So if you are answer of these three equations, you have to understand what is the topic mixture of ideal gases. Ideal gases. The first one is, does ideal gases exist in real life? Why we study ideal gases, and can real gas and ideal gas follows these equations. These are the questions to understand our chapter. So let us starting with this one. Let us starting with this one. So does ideal gas exist in real life? No. So we don't have, or we don't know that is ideal gases is exist. So the only, let us starting from the ideal equation, that the ideal equation is that's equal to PV equal to nRT, and this one is using for ideal gas, as we have to discuss in engineering thermodynamics 1, and PV that is equal to Z nRT. This one is using for real gas. Now the difference is starting here. That is the only variable is we have to see is Z. What is Z? Is Z is a compressibility factor. Compressibility factor. So the compressibility factor is Z. Is we have to find we using of the equations of PV over nRT. So this nRT is R is, that is the universal gas constant. Universal gas constant. So the only thing that is we have to finding of Z. So when you have to see in here is, the only difference is here is Z in real gases, but in ideal gases there is no any Z values. So if Z is equal to 1, this one is a real gas. Real gas that's equal to ideal gas. That means we have to treat it of this real gases as ideal gases before, because Z is equal, that is Z is 1, means that is directly real gases is equal to ideal gases. So when the Z value is 1, so when Z is equal to 1, thus Z is equal to 1, let us go to end scene. Let us go to end scene in our property tables and the charts of Lenson over generalized compressibility factors or compressibility charts. This one is, as you see in here, this one is a chart that's finding of Z. So when we have to Z, finding of Z is, that is PV over RT. So you have to using of the number of moles of nRT. So Z is a compressibility factor. So, and this graph is the y-axis that indicated for Z values, and the x-axis that indicated for reduced pressure of PR. And as this, when you have to see in this, the red curve is indicated for reduced temperature. Reduced temperature. So whereas simply we have to see in here is, that is the PR of the PR, that is reduced pressure and using of the reduced temperatures, and what is the Z value is approach to 1. So when the Z value see here we have to see is approach to 1, when the temperature of TR is increased out and the reduced pressure is decreased out and approach to 0. So the values is reached to 1. So we have to say that with the compressibility factor of Z is equal to 1, when that is TR is increased, and when is the PR is decreased out, or until reach to the values of around 0. So as we have seen in the first chapters, that is TR is equal to the temperatures at a given conditions of substances over using of a temperature of each substance critical point. Similarly, when we have to finding of a pressure of a critical point, a radius is, that is the pressure of a given substance at a conditions over, that's the pressure of a critical point. What is a critical point mean? What is a critical point means? A critical point is all substances that is changed to the in TS diagrams, that is a critical point is here we have to see as this point. So all saturated liquid is directly changed to in a vapor state. So when the saturated liquid is changed to a vapor, that is without considering as saturated liquid vapor mixtures, or simply saturated liquid is changed to the vapor or saturated vapor. So that is a point is we have to call it of a critical point. That a critical point in having of its own temperature and having of its own volume, and it is pressure by each substance. You have to see where you have to getting of this a critical point. This a critical point is you have to getting with this a critical point of pressures, a critical point of a temperature, and similarly when you have to see in as a critical points of volume, that is at a given condition of substance of V with a critical points of a volume of critical point. So when this a point of critical volume, temperature, and the pressures we have to finding as our table. So let us go to a table of critical points of each substances with our table. So our table indicates that all of substances having of its own critical points. So a critical point is have you seen here is all substances having of a critical point is here have seen is a critical points of a temperature, a pressure, and a volume. So for air, that is a critical temperature is 132.5 and a critical pressure is 3.77 and the volume one is given. All substances here that is have you seen or have you discussed with the first the engineering thermodynamics one, we have to see what is a pure substance. So this substance is having of its own critical temperature, critical pressure, and a volume. What does it mean? That is all the points with using of a PV or a TS diagram. All substances is changed to, that is, or substance is saturated liquid changed to a vapor one. That's a point is that is a critical a critical point. So we have to read in from this table and finding of our values of this z values. So this z values is that is equal to 1 means that is real gases is treated as ideal gases. So when z is equal to 1 is that is a tr or reduced temperature is increased with or high temperature, and a tr I mean a pressure of reduce, a pressure of reduce, that is the pressure of reduce is with low pressure. So with the gases at high temperature and low pressures, we have to treat it as ideal gas. Are treating us ideal gas. So what does ideal gas exist in real? No, but we have to treat it that gases, all the gases or real gases is treated as ideal gases by using of some conditions. That condition is treated of that air with high temperatures and with a low pressure. That's indicated for we have to getting of the z values or compressibility factor is equal to 1. So this one is that is ideal real gas and ideal gas having of the same values, the same values. So why you have to study of this ideal gases? Ideal gas. Why you study of this ideal gases? This ideal studies we have to having of with two reasons. The first one is why we study having of two reasons. The first one is to learn and understand the behavior of gas. One is to understand and learn about the behavior of gas. The behavior of gas. Second reason is why we study of ideal gas. Why we study ideal gas to calculate the properties of gas. Because of these reasons, we have to learn in ideal gases that real gas. We can also understand and learn the behavior of gases, but it's difficult to know what is the compressibility factors of each substance. So simply when you have to say is that is the compressibility factor is equal to one, that is the real gas is treated with ideal gases with the condition of high temperature and low pressure. So the one thing we have to study of these ideal gases is the only thing that is using of these two reasons to understand and learn the behavior of gases and to calculate the property of gas easily. So now let us come to our uh, chapter. Our chapter is a mixture of ideal gas. So in this chapter, we have thinking of five topics. The first topic is compositions of gas mixtures. Let us starting with compositions of these ideal gases or gas mixtures. So let us starting with compositions of ideal gases. Composition of ideal gases. Composition of ideal gas mixture. Let us starting with ideal gas mixture. So let us using of substance of A plus using of a substance of B. We have to getting is a substances or a mixture of A plus of B. So this one is substance. This one is also as a substance, and this one is mixture. So to study of this mixtures property, to study of this mixture property, we must know about the properties of this individual substances. So the properties of the substances, it may be any intensive or extensive properties, that is using of X, that is individual properties. Similarly, we have to using of other individual properties of substance of B. You have to make an of a substance of X plus of Y of a substance. So each substances of in a mixture is having of its own properties, but it depends on the substances properties, the substances properties. So we have to must understand this properties of a mixtures. We have to know about the properties of individual components. So to study this a mixture's property, to study of this mixture property, we have to use two ways of describing of this combustion mixture. Two ways. What are they? The first one is we have to say that is a molar analysis. The molar analysis. Second one is gravimetric. The second one is gravimetric. Metric analysis. Gravimetric analysis. So let us starting with gravimetric analysis or molar analysis. Molar analysis. If a substance of A plus a substance of B, that is we have to getting is a mixture of A plus of B. That is this one is a mixture. So in the molar analysis, we have to see that is the number of moles. So one mole of a substance of A mixed with using of, let us say, 2 mole of substance of B, we have to get in the summation of this two substances, summation of two substances moles. That means 1 plus 2 mole of a substance, that is equal to 3 mole of mixtures A, B mixture. So this analysis we have to call it is a molar analysis. A molar analysis. So a molar analysis of mixtures by using of this mixture or two substances mixtures, separation of two moles. This one is we have to call it is a molar analysis. Second one is that is gravimetric analysis. Gravimetric analysis. This gravimetric analysis is if you have to see that is substance of A and B that is making of a mixtures of A plus of B. So when having of 1 kilogram of a substance A plus 2 kilogram of a substance of B, you have to getting is 3 kilogram of a mixture of A plus of B. This one is that is you have to call it is a gravimetric analysis. A gravimetric analysis. We have to call it gravimetric analysis. That is using of two individual substances. Two individual substances. So second one today we have to see is that is any properties of A. Any property you have to see to study of in a mixture any property, let us say of x, that is x the power of m, as I mean a suffix of m is m indicating for mixture. And if any property of x using of a suffix of I is I indicating for a single component or a single component of a mixture. A single component of a mixture. Components of mixtures. So any substances that is using of the property of x, xm is m is indicated for a mixtures and I is using for a single component of a mixtures, a single component of a mixture. Because of that, that is a mass of a mixture as the analysis of using of gravimetric analysis, that is the mass of mixtures of M is summations of all individual components using of K components with using of mass of individual components. That's as told you before. We have to see of substance of A and B. That is summations of a mass of A plus a mass of B. A mass of B. This one is a mass of a mixtures. A mass of a mixtures. Second one is number of moles or a mole number of mixtures. Mole number of mixture. This one is a number of mole of a mixture is summation of all individual components. That is a number of mole of individual components with k elements. This one is similarly as seen in molar analysis. That is the number of mole of A plus the number of mole of B. This one is analysis of a mole, a molar analysis. That is the mole number of mixtures. The mole number of mixtures. So, based on this, the other thing today you have to see is that is mass fraction. That is, let us using of this one is a mass fraction. Mass fraction. Mass fractions is denoted by using of MF. This MF or a mass fraction is the number of uh, using for only using for a single component. This one is using for a single component. So for a mass fraction of individual components of I, this one is equal to the mass of individuals per the mass of a mixture. How much of masses of individual components occur in a mixture? That means so the mass of individual components over the mass of a mixtures for each component. Assume before that having of two uh, a mixture of A plus of B. So the mass fraction of A is the mass of A over the mass of a mixture. This means that the mass of A is over the mass of fraction of A mean that is a mass of A that is over mass of A plus of mass of B. This one is the mass of a mixture. This one is for individual components. The other one is that is mole fraction. Also, this mole fraction is using of a letter that is yi for each individual component. So the mass the number of mole of or a mole fraction of yi is equal to the number of mole of individual components over the number of mole of mixtures. So similarly, as shown here, that is when we have to study or when we have to see or we have to make it of a mole fractions for a component of A. This one is the number of mole of A over the number of mole of A plus the number of mole of B. This one is the number of mole of mixtures, the number of mole of a mixture. Similarly, we have to finding of the number of mole of fractions of B. This one is equal to the number of mole of component of B over the number of mole of A plus the number of mole of B. This one is, as told you before, the number of a mixture. So the number of mole of a summations of the number of mole fractions, that is yi, is the number of the summations of each individual component we using of a mole fraction is equal to 1. Similarly, the mass fractions of all each individual components of a mass fraction of individuals of the summation is equal to 1. Equal to 1. So we have to finding how much number of mole is occurring in mixtures and how much mass of individual components occur in mixtures. Mixtures, that is, we have to calculating what is a mass fractions and a mole fractions, a mole fractions. And the other thing we have to see today is molar mass. Molar mass M is denoted with using of a molar mass of all individual components or a mixture is this one is equal to mass over of number of moles. We have to using for individual components or a mixture one. We have to see for a mixture one is a molar mass of a mixture is that's equal to a mass of a mixture over the number of mole of a mixture, or we have to see using of the molar masses for individual components. This one is equal to the mass of individual components in a mixture over the number of mole of individual components. Individual components. So we have to see in here is in a molar mass of a mixture is a mass of mixtures over the number of mole of mixtures. So what is the number of mole of mixture is that is all summations of mass of individual components that is having of each individual components over the number of mole of mixtures. The number of mole of a mixture. So this mass of a mixture, mass of individual components, that is the mass is that is equal to a molar mass times of a number of moles. So when we have to using for individual components, the mass of individual components is equal to the molar mass of individual components and the number of mole of individual components. Let us substituting at summation there is a mass of individual components. So summation of all individual components, that's using for a mixture, that is the molar mass of individual components and the number of mole of individual components over the number of mole of a mixture. So now we have to see in here is that is the number of mole of a mixtures, that is the number of mole of a mixture individual components over the number of mole of a mixture is we have to see in here is mole fractions, mole fractions. So a molar masses in a mixture is we have to calculate it as using of the summations of all individual components times of a molar masses of all individual components times of the mole fractions of individual components, because that's the number of individual components over the number of mole of a mixture is a mole fraction. So you have to calculate of this molar masses. The molar masses or all each component is having of its own molar masses, having of its own molar masses. So we have to finding of the molar masses from by using of these equations. These equations. So the other one is a gas constant. A gas constant. So what is a gas constant? What is the value of a gas constant? Mostly we have to know is air gas constant. air gas constants, but gas constant is R, that is RU, is universal gas constant. This one is universal gas constant, and the values is 8.314 kilojoules per kilograms Kelvin, I think. This one is the universal gas constant. But in a gas constant of that is apparatus gas constant for each substances or average or apparatus, apparent gas constant for using of each components or in it as using as a mixtures of this a gas constant is always you have to calculate with using of universal gas constants over the molar mass of molar mass of mixtures, or in each individual components using of Ri or air or water or any substances, we have to calculate of this gas constant is Ru over molar mass of molar mass of individual components. So for making of a check for the gas constant of air, you have to calculate it from using of universal gas constants Ru over the molar mass of air. Let us checking of the values. That is, we have to read from a table. From a table, let us checking of air one. As seen here, air that is having of a molar mass and a gas constant. So let us using of this molar mass and the universal gas constants. So we have to getting of the values of this gas constant. So the gas constants are few seen here is 0.287 and a molar mass is 28.97. Let us using of this values and calculating of our uh, gas constant. So what is, as told you before, what is universal gas constant is that is 8.314 and molar masses that is around 28. So when we have to calculate out of the gas constant is 0.287. So let us calculate of this Ra using of or gas constant of air is gas universal gas constant is over molar masses that is 8.014 over around 28. So let us calculate using of a calculator. Let us using of a calculator. There is 8.314 divided by 28. So we have to get it is 0.29. 0.29. So 28.97. 28.97. Let us put in the molar masses 28.97. 28 8.314 divided by 28.97. So we have to get it is 0.286. 2 points. So now we have to getting of gas constants. That's a value. So for each we have to calculate of a gas constant using of gas constants, universal gas constants and molar masses. This one is also about the first topics of our uh, unit, that is a composition of gas mixtures. Composition of gas mixtures. So in the next video we have to do some examples. Until now, thank you. If you have any questions you have to put in, I will try to uh, explain the questions behind regarding to the compositions of mixtures. Until we have to meet in the next video. Goodbye. Thank you for your attention. Don't forget to subscribe our channel. Thank you.